So we have to apply now. Next step is to apply this to the sequence of secant numbers, the A sub n, called Euler numbers. But Euler numbers, there are so many kinds. So those are the secant numbers and the tangent numbers. And so, well, the secant numbers, if you take the secant function and expand it, the Taylor expansion, the coefficients are positive integers, and are called the secant numbers. So in sum, this is number A1, 2, 2, 4, 5. For the tangent numbers, so it is very classical. It goes back to Euler. Euler already knew all this, you see, no problem. So we are still in the 18th century. So now the Taylor expansion of the tangent, we do have this sequence of numbers, which have high powers of 2. And so how to apply the gradient trick to those two sequences? Oh, first of all, first of all, if we need formulas for tangent or secant numbers and Bernoulli numbers, this is a Bible. This is very much written in the spirit of the 19th century, even though it was published in 1923. And it's very convenient when you have to refer in papers, you see, people who reinvent new identities and Bernoulli numbers. So you have to take the pages of that book, and usually you find the solution. So it's very helpful when you are a referee to have this kind of book. So I strongly recommend it. It's written in French by a Danish mathematician, and so it's very useful. You find all that you need. So work out a PQ analog. In other words, I have to reconstruct the previous diagram for sec of u and tangent of u. So now, we progress. Now we have reached the 20th century, and Father Jackson introduced the Q sign and the Q cosine by an expansion by the sum of those Q series. This is explicitly defined in Gasper and Raman, not in George Andrews and Askey. They disregard the Q sign, they disregard them, but it's explicitly, as in an exercise, explained in Gasper and Raman. And so this exists already. So this is going to be the first step. So we have the cosine of u, and now we have the cosine q of u. So the horizontal arrow is going to be defined. So, and then the q tangent. Well, the q tangent are, well, you see, you take sine of q divided by cosine of q, secant 1 divided by cosine of q, and then you make the expansion in q series. So in other words, you write this in the q series by making this kind of normalization. So this is not defined in Gasper and Raman. Gasper and Raman love cosine and sine, but disregard tangent and secant. Have T, well, studied Einstein, not so much. Only in scattered paper. Richard Stanley, yes, in his paper in 26, he studied them. I don't see him, but he's somewhere in the audience. Oh, yeah. Okay, so there was the paper by Andrews and I guess so, and some others. And I remember there was a talk by Schütz, not a talk, a private talk, back in 35 by Schütz. So, but in fact, surprisingly enough, it's not in a written book. So we have to look for those papers at least. And what Andrews and Gessel have done, essentially they've studied the fact that those polynomials were divisible by monomials of the form 1 plus q to the I. Oh, that's it. Okay, so that's it. We have the first. Give a table of the first polynomial. That's a good principle. So you see, T5 is already divisible by monomial of this, by polynomial of this kind, and T7. Look at this T7. They are very divisible by this kind of stuff. And for the Q secant, that's there is an extra term plus something. So this, and now, yes. Okay. So that's a good start. That's what I want to say. It's a good start because we have this. This is classical. This is the definition of the secant number and the tangent numbers. And then we have secant of q defined by this. So that's a good start. So we are done with the horizontal arrow. So this is okay. We take that. So this has been defined. But now the problem is we have to work with the vertical arrow. So in other words, we have to invent a sequence of series of this kind in such a way that we have the limit of this equal to that. So this has to be invented in some sense. There are many possibilities. We have two requirements. First, we must have that limit. And now what we obtain, this must be a series. This must be a series for which the coefficients are polynomial with positive integral coefficients, if they exist. Okay, so well, the natural thing to say or to write. So instead of having q equal 1 here, let's replace this. Okay, let me go back to here. So this is tangent q of u. This is tangent q of u. So what we are going to do now? We are going to define this kind of sine q. So if we had q r equal 1, this would be sine of q. So let's just, what we have done, we put r in here and we sum. Okay. Then we can define secant r of q, those two. And verify. Oh, it's not a big deal. If you're an analyst, no problem. If you're not an analyst, no problem either. So it's, and then, oh yes, we have what we want. Now, now we have those functions, and we must prove that by expanding this into a series of this kind, you must study, you must see what those polynomials are, what those coefficients are. And the problem is, now the next step would be to prove that those coefficients are polynomials in two variables T and Q with positive integral coefficients. And so now it's going to please Doron because I'm not going to give an analytic proof because I don't have one. So I'm waiting for true analytical proof. I'm going to give a combinatorial proof. So this is one of the examples where combinatorics precedes analysis. So so this is the same diagram for tangent. So for tangent, here we have the classical Q tangent, and here we have the tangent Q of R I defined before. And when we expand this series in the Q series with this normalization, then we have to study those coefficients. Okay, look, and then when you have done this, you rush to your vehicle program, not me, but usually my companion. My trouble was, when I used to work with Doron, he was such an expert in computing, so I didn't have to learn many problems.